In the previous videos, we were focusing on the qualitative properties of solutions. So we're going to wrap up the topic of solutions by taking a look at how we can measure the concentrations quantitatively. There's different ways one can measure concentrations. Outside of chemistry, percent concentration is the most common way people do that. And if you recall, percent is basically just the part over the whole times 100. So in a percent concentration, the part is the amount of solute that we have, and the whole is the amount of solution. Now we can measure the amount of these two things in different units and give us different types of percent concentrations. For example, we can do a weight volume percent. In a weight volume percent, we're measuring the solute by weight or mass, normally in grams, and we measure the volume in milliliters. There's also a volume percent, and in that case we measure both the solute and the solution in milliliters. And the third possibility is a weight percent, where we measure the mass of the solute and the mass of the solution both in grams. So when do we use a weight volume percent? Well, most commonly when the solute is a solid and the solvent is a liquid. And a good example of that are various IV solutions. This represents what they call a normal saline solution, a 0.9% sodium chloride solution. So this is in this case, sodium chloride is our solid solute and water would be our liquid solvent. So we can calculate a weight volume percent pretty easily. Suppose we dissolved 4.5 grams of salt in enough water to produce 500 milliliters of solution, and we wanted to figure out the weight volume percent. All we have to do is put the grams of the sodium chloride on the top and the milliliters of solution on the bottom, simply multiply that result by 100, and that comes out to be 0.9%, which is the concentration of a normal saline IV solution. The volume percent is logically used when both the solvent and the solute are liquids. A good example is any alcoholic beverage, so wine, beer, whiskey, all of those things, they measure the alcoholic content in volume percent because the alcohol is a liquid and so is the water that it's dissolved in. Now, in addition to just calculating these percentages, you can use a percent as a conversion factor because these percentages are in fractions, so they're in the same form as a normal conversion. So for example, if we had this bottle of red wine and we knew that it contained 750 milliliters of wine and we wanted to know how much alcohol was in there, we could use this percentage as a conversion to calculate that. So we set it up like any conversion problem. We start with our known amount, which is the volume of the wine, and then we use the percentage, the milliliters of alcohol, in each 100 milliliters of wine, because remember, that's what percent means. Percent means out of 100, so 12% means 12 out of 100. The milliliters of wine cancel out like any conversion should, and we end up with the volume of alcohol. Weight percents are really only commonly used in science. Chemists use weight percent for a very simple reason. They're accurate. If I wanted to measure out 100 milliliters of water, I know the density of water is 1 gram per milliliter, so I could measure out that 100 milliliters in a graduated cylinder, and I might be able to get it to within a tenth of a milliliter. If I weighed that same water on one of these balances that weighs out to the nearest thousandth of a gram, I could be 100 times more accurate. So chemists commonly use weight percent simply because we have readily available, accurate electronic balances, and they do give us more accurate measurements. So if I wanted to calculate, say, the weight percent of a sodium hydroxide solution, if I had 157 grams of sodium hydroxide and I dissolved that into 355 grams of water, I could calculate the weight percent. In the numerator would be the grams of sodium hydroxide, and the denominator would be the grams of the solution. So you notice I didn't put the 355 grams in here because that's just the solute and just the solvent. I need the solvent and the solute together, and that adds up to 512 grams, and that gives me about a 31% weight concentration. In chemistry, we most commonly measure concentration by molarity. Molarity is simply the number of moles of solute per liter of solution. And of course, the reason chemists like to use molarity is because all of our chemical reactions are measured in moles. So it's very convenient if our solutions are also in moles. It makes it real easy to relate the amount of a solution we're using in a reaction to the amount of moles of the substance in the balanced chemical equation. So, for example, suppose we wanted to figure out the molarity of our normal saline solution we used an example a few minutes ago. It's relatively simple to go back and forth between the different kinds of solution concentrations. So our starting point would be the normal saline solution. So 0.9% means 0.9 grams of sodium chloride in every 100 milliliters of solution. So this is our starting point, and this is our target. We want moles over liters. We've got grams over milliliters. So if you look at it, it's actually two pretty simple problems. The first thing we need to do is change the top, the numerator, from grams to moles, which we spent a lot of time doing back in chapters 9 and 10, using the molar mass of the substance. And then going way back to chapter 1, we simply need to change milliliters into liters. So our first step, we're going to convert the grams of sodium chloride into moles of sodium chloride using the molar mass of salt as our conversion. The grams of sodium chloride cancel out, and now we're halfway there. We have moles on the top, which we want, but we still need to get liters on the bottom. So we'll add a second conversion here of 1,000 milliliters per liter, and now our milliliters cancel out, and we end up with moles on the top and liters on the bottom, and that gives us moles per liter, or we simply use the capital M, which is an abbreviation for molarity. So in summary, we now have 4 different ways of measuring concentration. Molarity, which we just talked about, moles in the numerator, liters in the denominator. We also had our 3 different kinds of percentages, our weight-volume percent, and our volume percent, and our weight percent. Going back and forth between these is relatively simple. For example, if we wanted to go between, say, a weight-volume percent and a volume percent, the numerators are the same, so we wouldn't have to make a change there. All we would want to do is change the grams of solute into milliliters. Well, how do we go from grams to milliliters? That's a simple density problem, and we would, of course, need to provide the density. Same thing is true if I wanted to, say, go from a weight-volume to a weight percent. I would need to get these milliliters on the bottom into grams. And again, that would be another density problem. And, of course, we just did one with molarity. If you want to get from, say, a weight-volume percent to molarity, we simply need to get grams into moles and milliliters into liters, and we could obviously do the opposite. If we had molarity to start with, we could change moles to grams and liters to milliliters. So let's try a few practice problems. All right, for our first problem, let's consider a sugar solution. So we have a sugar solution. Sugar is C12H22O11. and it has a molarity of 1.375 and a density of 1.1785 grams per milliliter. I'd like to calculate both the weight volume and the weight percent of the solution. With a solid like sugar, we can't do a volume percent because you can't really measure the volume of a granular solid like sugar. If we have liquids or gases, we can do volume percents, but with solid solutes, normally that's not possible. So, for the first problem, let's figure out what the weight volume percent is. So we'll start with our molarity, that's our given. If we want a weight volume percent, we need to turn the moles into grams and the liters into milliliters. So our first step, let's convert moles to grams. If you add up the mass of all 45 atoms in that formula for sugar, it comes out to be 342 grams per mole. So we've got our moles to grams. Now our next step is we need to change the liters into milliliters. So we're going to put liters on the top so they cancel out, and milliliters on the bottom. And that will leave us with grams on the top and milliliters on the bottom. And all we'll have to do then to get our percentage is multiply by 100. So if we check our calculations here, our moles that we started with cancels with the moles in our molar mass. The liters that we started with cancels with the liters in our second conversion, and we end up with grams over milliliters, which is a weight volume percent, and that comes out to be 47% weight volume. To get the weight percent, we can just pick up where we left off here. We can start with that 47% weight volume percent, which means 47 grams of our sugar in every 100 milliliters of solution. So we've already got our numerator in grams, so that's good. All we have to do is get the denominator in grams. And as we said a little bit ago, to get from between milliliters to grams or grams to milliliters, that's going to be a density problem, and the density was provided. So all we have to do now is use the density. We're going to put milliliters on the top so they'll cancel, and we'll put grams on the bottom because we want grams over grams in the end to get a weight percent. And we simply then multiply that result by 100. So the milliliters we started with cancels with the milliliters in our conversion, and we end up with a 39.9% weight percentage. And of course the weight volume and weight percent will normally be different unless the density happened to be 1. If the density were 1, it wouldn't make any difference, but that's rather uncommon. So usually the density is different than 1, and those two percentages will not be the same. Rubbing alcohol is a solution of isopropanol or isopropyl alcohol in water, and it's commonly sold in the grocery store or drugstores as a 70% volume solution. So given that, let's see if we can calculate the weight volume percent, the weight percent, and the molarity. And to do that, of course, we're going to need some more information. We'll need the molar mass, which we can get from the chemical formula, and we'll need both the densities of the alcohol itself and of the rubbing alcohol solution. So let's start out with calculating the weight volume percent. So we already have the volume. 70%, of course, means 70 out of 100. So our denominator is already in milliliters, which is what we want. All we really have to do is change the numerator into grams. And of course, to change milliliters into grams, we need the density. So in this case, we're going to use the density of the isopropanol itself, not the alcohol solution, because we're trying to change the numerator. So we multiply it by the density of the isopropanol, and then simply multiply by 100 to get our percent. If we take a look at it, we can see that the milliliters of isopropanol we started with cancel with the milliliters in our density, and we end up with a 61.5% weight volume solution. To get the weight percent, we can just pick up where we left off in the first problem. So we'll start with our 61.5 grams of isopropanol in 100 milliliters of the solution, which is our weight volume percent. In this case, we need to change the denominator. It has to go from milliliters to grams. The numerator is already in grams, so we're fine there. So this time we're going to use the density of the rubbing alcohol solution itself, since that's what we're trying to change. We'll multiply that result by 100, and that will give us our percent. So in this case, the milliliters in our first step cancel out with the milliliters in the second step, and this time we end up with a 68.7% solution based on weight. And then finally, we can calculate the molarity. So molarity, of course, is moles per liter. So the easiest place to start is probably once again with our weight volume solution. We have grams and milliliters. We want to get to moles and liters, which means the grams needs to be changed to moles and the milliliters needs to be changed into liters. So our first step is to figure out the molar mass of isopropanol, which is 60 grams, and we can use that to convert grams into moles. So we've got the top where we want it. Now we need to do the bottom. We need to change the milliliters into liters, so we have our 1,000 milliliters per liter. We can cancel the grams of isopropanol in the first step with the grams in the second step, and then we can calculate the milliliters in the first step with the milliliters in the third, and we end up with moles on the top and liters on the bottom, and that is exactly the units that we should have for molarity. So you can always write molarities as either moles per liter, or you can use the capital M, which is simply an abbreviation for molarity or moles per liter.